So yes, hello everyone. I'm Quentin Manière, and together with Meghyn Bienvenu and Michaël Thomazo, we wrote an article dealing with answering counting queries over DL-Lite ontologies. And so the framework we're investigating is one that is ontology-mediated query answering. The point is to connect a user with several data sources. So to do so, we put in the middle an ontology expressed with description logics. And the most common queries investigated are conjunctive queries that are mainly asking how to satisfy a condition. And what I will tell you about is a natural extension that is counting queries, asking for how many ways to satisfy a condition. So we'll consider two dialects, DL-Lite core and DL-Lite air, which are well known to have good computational property with conjunctive queries. Okay, so let me dive in with a toy example. So our data are represented with an A box involving roles like this one here. I think that Alex is a fan of Bill, or concepts. On the fourth line, Bill is a musician. So on top of this, okay, it's easy to represent with a small graph. And on top of this, we put an ontology that is a T box. And so, for example, the first axiom is stating that any musician must be inspired by someone. So you can already see that our knowledge is somehow incomplete because Carol is a musician, but we don't know any person Carol is inspired by. So we need the notion of model you're probably familiar with. So here's one. It's just one way to complete the A box to comply with all the axioms. And here's, you can have several models. Here's another one. And I will assume you're familiar with all of this. And the notion of query we'll be investigating, as I just said, are counting queries. So you start with a conjunction, which is of concepts and role atoms that might involve either constants or variables. And we distinguish three kinds of variables. The first is answer variables, which you probably know about. And then we distinguish between existential variables and counting variables. The idea between these are that you want to count the possible values for counting variables among all the homomorphism you can find of your query into a model. Okay, so you don't care about the number of different values for the existential variables, but you're just considering the possibilities for the counting variables. So you can simplify just a little bit the setup by removing, for example, by removing the answer variables. Somehow you obtain Boolean counting conjunctive queries. And here's in this example, you can see that it's a query trying to find out how many artists are listened to by Alex's icons. And so regardless of how many icons are listening to an artist. Before I go further on this, let me say a really short word about the related work. So our starting point was an article by Kostelev and Reuter, which was introducing two different kinds of counting queries, namely count and count distinct here. And what I already showed you is a generalization of both these two kinds. But one of them was also the starting point from other articles, also real recent, and which was investigating some restrictions about queries and ontologies with this kind of counting queries, and also introducing some query writing techniques. And all this also is really close to the notion of conjunctive queries over back semantics, as back semantics is somehow already counting. And furthermore, it's really interesting to notice that other semantics were investigated. For example, we have the epistemic aggregate queries, which was more focused on having the counting queries mapping on individual names. Or more recently, this one, which was dealing with counting the number of certain answers, where certain answer is the classical notion of certain answers you probably know about. Okay, so let me clarify our semantics. So as I told you, the idea in one model is to look at all the homomorphism we have of our query into our model. That's also called a match. And we only keep the values for the counting variables, that is a Z tuple. And then we count them, and that's our answer in this model. So as an example, here, this is a query I already showed you, and this is the first model I presented you. So in the bottom left, I'm trying to find the answer of this query in this model. And we start by first homomorphism, so our constant is mapped on its interpretation, y can be mapped on b, and z can be mapped on c. And I only keep the value for the counting variable v, so I only keep c. I can do the very same by reaching the value d. I keep this value, and it's interesting to mention that you can also reach anonymous values. So this one here, bottom one, can be reached. So I'll consider it. And here's an example of y being, since y is an existential value, here you can see that there is another homomorphism allowing to reach this anonymous element with the variable z. But since y is an existential value, it doesn't change our answer, which is in this model 3. So we can do the very same with the other model I showed you before, and I'll go a bit faster on this. But the main point that you have to observe is that in this model, the answer is 2. So we really have to deal with different answers coming from different models. And to take this into consideration, we'll introduce the notion of certain answer. And in this context, a certain answer is an interval such that whatever the model you're considering, the answer in this model belongs to your interval. So from the example above, you can convince yourself that 1 plus infinity and 2 plus infinity were certain answers. Whereas since we found a model in which 2 was the answer, 3 plus infinity cannot be a certain answer. So here you might be interested in somehow the most relevant certain answer, here 2 plus infinity. And this is a really interesting related question, which we call the tightest certain answer, and I'll tell you more about this later. Now a word about the dialects we'll be investigating. So we'll focus on 2 well-known DL-Lite dialects. So remember that starting from atomic rules and atomic concepts, you can build more, considering either the inverse rule or the projection on the first variable. And you can also put some negation. And what I really want you to remember is that in DL-Lite core, or first dialects, you only allow concept inclusions with this shape. And with DL-Lite error, you also allow role inclusion with this shape. Okay, and I'll also tell you a word about the way we measure complexity. So the problem we're trying to decide is, if a candidate interval is indeed a certain answer for a query over our knowledge base. So the classical combined complexity notion where we can put everything as part of the input. And you can also be interested in understanding how this scales with the size of your data. So you can just consider the ontology and the query as constant, and so that is the very same problem. Here you may wonder why I'm talking about this kind of intervals, m plus infinity, instead of any interval as I mentioned before. And the reason is that with the 2 dialects we're considering, the axioms are not cannot restrict the size of models, which means that the values for the upper bound are either 0, 1, or plus infinity. And only plus infinity is a non-trivial case. So that's why we're considering it in here. Okay, now a word about the complexity results we obtained. So first we started by generalizing the results from our starting point. And as you can see, in data complexity, both dialects, it's quite hard. It's coherently complete, so quite intractable. And in combined complexity, it's even harder, and still there are still some gaps. So it's still unclear. And a first direction to try to improve these complexity results is to restrict the family of query we're considering. So we tried with rooted counting conjunctive queries, in which you ask for each connected component of your query to contain either an answer variable or a constant. So here's a small example. On the left, you have a constant, on the right, an answer variable. But in this context, it doesn't help, and the complexity results are the very same. So we digged a bit further by considering what we call the exhaustive rooted CCQs, which are rooted, and also we no longer allow existential variables. which is not much of a restriction actually, because it's only thing that you will count all the quantified variables values, possible values. And actually it was also the starting point for other articles. So it's still a big class of queries. And what's interesting with this restriction is that with the direct DL-Lite core, we were able to pinpoint the exact complexity the exact complexity in both data and combined, and including TC0 complete situation in data complexity, which is known to be tractable as below log space. I can tell you a word about how we do this. So in the latter case I mentioned, so with TC0 and PP complete situations, among others, a key property is that the minimal amount of possible values for the counting variables is reached in a well-known model, which is the canonical one. So it allows to ease the decision of the problem. And in the other case, we're interested in the complementary problem, which is trying to find a counter model in which the answer is outside of your candidate interval. And we want to guess this model, and to do so, you need to ensure it has a bounded size. And sometimes this size is polynomial or exponential, even double exponential in some situations. That's where this bound comes from. And about the lower bounds, I will only tell you about the CoNP lower bounds you can see here. It comes from a reduction from graph coloring problems. And at some point, you need your query to count the colors used by your graph to ensure it's not using too much colors. And somehow it makes your query disconnected. And you can still simulate this disconnection with existential variables in this situation, or with role inclusion in the second situation. But when both are dislocated, you can no longer. That's why it becomes in TC0. Okay, a word about the variant I mentioned before, which are the tightest certain answer question. So instead of
just to interject quickly, about 1 minute left.
Yes, yes. So, okay, the tightest answer, you need to be a certain answer, and you need, if you go a step further, you're no longer a certain answer. So it's an optimization problem, and what we were able to prove is that, okay, whenever you start with a CoNP complete setup, you expect it to be, well, you know it will be in DP, and the question is it DP complete? And we were able to prove that it's always a case. That is, whenever we start from a CoNP complete situation, we have a DP complete situation. And okay, which was closing a question left open in the by your starting point. And what about ongoing and future work? So first step would be to close the remaining complexity gaps we have in a combined complexity. On the other hand, in data complexity, we identified a tractable case and several untractable cases. So we may want to, it would be interesting to have a full classification of what happens in between this case. And we can also investigate other description logics by adding some coordinate restrictions or functionality actions. And we also already know that our CoNP hardness results extends to EL. It might also be interesting to generalize to other aggregate queries, as our semantics is quite naturally extends to this. And in the tractable case we identified, it might be interesting to have actual algorithm, for example, by investigating query writing techniques. So thank you for your attention, and I'd be glad to answer some questions.